Okay, so we're in LISE Geo4 and the PL optics table. This is a documentary for the new Photoconductivity rig, and so I'm just going to walk through what we have here in case anyone has questions. If you do have any further questions, you can contact me, Robert Gustafson, at rigustafson@cs.harvard.edu. Okay, so first and foremost, the benefits of this photoconductivity rig is we are using a broad spectrum from the xenon lamp source here, and that is led through a liquid fiber output to here, and it's sent through a condensing lens to a focusing lens onto a McPherson 2035 monochromator. It goes in, it comes out on the other side into two achromatic lenses, 35mm diameter, to focus it onto the chopper wheel so that we can efficiently chop it, and then that is then sent out and focused again onto currently, which is a detector, but in the future would be your sample, either for room temperature measurements or in this handy dandy cold finger. If you haven't used this before, there is a window here where you would put your sample on, and then you can see here that you would then make, it's not coming out very clearly, but you can then make contacts with these towers that you might be able to see. There you go. And there should be already two magnet wires soldered on that you should solder your sample to, and then the data will come up here out this port. Use the correct connector that splits into two two coax cables labeled A and B. Your signal will come out. One of those will be your ground, the other will be your signal, and with that you need to send it currently into this pathetic looking circuit board. The banana clips here are for the signal in, this one, the red and black combination of signal in. These orange and red are signal out. Make sure that you don't accidentally switch which one is which. Note always that in both cases the ground is the black wire. Also on these BNC adapters, this little notch on the outside here where my pinky is, that's the ground side, so make sure that's connected to ground. Currently the trans impedance is set to 100 kiloohms by this resistor here and this resistor. This resistor determines your gain. Your gain is equal to whatever resistance value it is. If you want a gain of 1000, make this 1 kiloohm. You also need to match it to this resistor here. This resistor compensates for any thermal effects at the input pins to this op amp. The rest of the board, just ignore it. Those are stray circuit elements that never made it into a finished product. Another thing is, this is the power supply here, these two buttons. So if you push this forwards towards the connectors, that turns power on to the op amp, which then can give you a voltage output. The off state is straight up or back towards the camera. So just remember to turn that on before you connect to a sample. And begin measuring. Otherwise, it's possible that you could overheat the op amp or destroy it through overvoltage. Okay, these are also 9-volt batteries, so you're running at approximately now plus and minus 16 volts on the rails of the op amp. And just be careful. You can see here these bare wires, those are live coming into the switch here, so just don't go touching there. This BNC cable from the amplifier then goes into the lock-in, which I'll show. Just goes into the lock-in. You run the BNC from the chopper controller that says ref output into the correct external reference on the front panel of the lock-in shown here. In the back, there's a BNC cable connected to channel 2, which is currently set to record the magnitude of the output signal. You should just leave that where it is, and that connector then goes into the oscilloscope, for which data is then sent via USB to this laptop here. This is the control panel. You have a point measurement, scan measurement, calibration, and then the program controls. When you start this program, titled Roberts Main 2, under the 789-A3 LabVIEW driver folder, the first thing you should do, if you have not done this before, is to make sure that the calibration is correct for the wavelengths that you want to measure over. What has been done in the past so far is to just do single calibration with a Heaney laser at 633 nanometers. The first thing you do is you click reset. What that does is it moves the grating to the lowest position, the lowest counter that it can, which is into the UV range, and then moves it back up to whatever home count number this is set to. Once it gets there, it waits for you to decide whether that counter number here corresponds with the wavelength from your input reference, which in this case is a 633 or 632.8 Heaney laser, and you determine that based on the voltage here. You can go to this home position and then add or subtract any number of counts from this until your voltage output is at a maximum that corresponds with your driving wavelength. Once you are satisfied that you have reached a maximum and that the counter number here corresponds with your wavelength, click set. That then sets the new counter number as the home position. If you want to see a single wavelength, you can then go over here to target position, enter in the equivalent wavelength that you'd like to take a look at, and then say set position. That will make the monochromator go to that wavelength based on the calibration wavelength and the difference in the number of steps, or these counts. It's a simple linear transformation. It does not take into account any dispersive effects of the grating. If you want to record what the voltage output is, click measure. That will then tell you what this is, and you can write it down. You can decide whether you want to take a single or continuous measurement, and continuous will just keep outputting a voltage every second or so, whereas single just gives you 1 voltage output at a time. Make sure that you have the correct grading selected. Currently it's 300, but if you were to change that, make sure you do so there. If you want to do a scan measurement where you scan between wavelengths, set your beginning here, your end here, your increment between steps, how many samples you take to average over for each step to obtain a resultant voltage from a current, and then the delay to give the electronics time to settle. After you're done with the measurement, you can click Save here. A prompt will come up to give you a location to save the text file that has the wavelength and the corresponding voltage. If at any time you wish to stop what you are doing, you can click Stop. That will bring you back to the default waiting period, where you can then scan again, calibrate again, or take a point measurement. If you wish to exit completely, you can then click Exit, and that will run you out. If you want to look at the graph of a scan measurement, you can click here where it says Graph, and then take a look at the data as it is being plotted. Occasionally there is a pop-up that says something like, I don't know what's going on, but this is a strange error, and it gives you 3 different buttons to click. Just click Continue. I do not know what this error is, but it's irrelevant, and ignore it. And your measurement will proceed again after that's over. So that's all for now. I hope more is to follow. And if you have any questions, again, contact me. Alright.